Hi, good morning, all. Good morning. I know it's not 9:05, but I just letting you all know that we'll be starting class at exactly 9:05. And well, good morning to everyone as usual. Welcome to physics class. And for the people on YouTube, right? Try your best to come across on the Zoom platform, right? Because when you're on the YouTube platform, you can't participate in the class games and whatnot. You won't be able to vote and whatnot. So I'm going to put the Zoom link on the Zoom. Sorry, I'm going to put the Zoom link on the YouTube chat for you guys to come across because there's lots of space on the, on the Zoom platform. And it's a much better platform, right? So that's a message for the people on YouTube. I send the Zoom link about 4 times on the YouTube chat, right? So come across, guys. The Zoom platform is always better. And for those who are worried, today's topic, we're starting it from scratch. We're actually doing magnets and electromagnetism. Okay? So once you know what a magnet is, that's the thing that attracts iron, and you know it have a north pole and a south pole you'll be able to follow along today. Now, I'm hoping to finish the whole section of the syllabus on magnetism and electromagnetism and actually do some past paper work coming down to the end. Right? And don't worry if you're in Form 1, Form 2, or Form 3, you're going to understand the work. Just pay attention, take notes when I tell you to take it down, and you'll be fine. All right, so we still have about 2 minutes and we'll start class at that time. All right, so you're relaxed in the meantime. All right, so it's 9:05 on the dot. Okay. So before we actually get started, remember, yeah, for those who attended yesterday's class, you were asked to join a team, right? And well, we were playing for points, either on the red team, blue team, yellow team, or green team. Now, if you were here yesterday, you cannot change your teams, whichever team you chose yesterday, you're stuck with that team for the rest of summer. But there are a lot of new people in class today, right? And well, before well, what we're going to do, we're just going to take another vote today just to see how much people on which teams again, because I'm hoping that we get more people on the red, yellow, and green team because the blue team usually seems to win the popularity contest, right? But before we do that, turn to a brand new page in your book. It should be a brand new book. Today's the first day of physics class. And take down today's topic. Write it down at the top of your page. Magnetism and electromagnetism. Right? That's the first thing you're going to do. Magnetism and electromagnetism. Right? You have a lot of drawings to do today, so make sure you have a ruler, make sure you have a pencil. If you have different colors of inks, like red ink, blue ink, or different color pencils and whatnot, it could actually make your diagrams look, more attractive, obviously, today. All right. So that's today's topic, magnetism and electromagnetism. For the brand new people in class, and like I said, there are a lot of brand new people in class today. These are the four teams available to choose from. Is take a look and you're going to be able to vote just now. It's either you're on the red team, the blue team, the green team, or the yellow team. Take a few seconds and, see which one appeals to you the most, right? Just see which one appeals to you the most. And we're just going to take a vote again. Remember, if you were here yesterday, you have to vote for the same team you picked yesterday. No traitors. If you're on the red team, you're on the red team forever. All right? So let's do the polls again. No? They're just for fun, right? Which team are you on? Let's just settle this. This week, we'll always be voting just to make sure everyone's settled into a team. Right? Yeah, I'm gonna get a lot of hate messages for putting yuck by the word blue. As you all can probably figure out. I'm on the green team, by the way, and every time I do this, the blue team wins. So I have a kind of have something against the blue team. All right, so we're gonna close off the votes there because I want to get started with class, right? By now, everyone should have reached. Just to show you the results, right? The blue team has still won as usual with 39%, but we got a lot of red, green, and yellow. So the red, green, and yellow teams are not far behind. All right. So let me just stop it. Make sure you remember which team you're on. And in case you forgot, guys, right? In case you forgot, this was the scores we left yesterday's class with. Your red team is on 16 points. The blue team is in first place with 25 points. Green team, my team, 0 points. And the yellow team, 18 points. Okay? So that's the standings at the moment. For those who don't know how to get points for your team, I'll explain how to do that later on in class. Let's get started, right? Let's officially get started. So the first thing we want to do, well, we're discussing magnets first, right? Now, don't draw anything as yet, all right? Believe it or not, one of these diagrams has a mistake in it. Do not draw as yet. I need you to listen. So what is a magnet? Well, when people talk about a magnet, it's usually what you know from everyday knowledge. A magnet is something that attracts iron. And the basics with a magnet is that it has two sides with two poles. It has something called a north pole, N for north, and S for what? South. And from common day knowledge, a north pole and a south pole are opposites, like how black is the opposite of white, or tall is the opposite of short, or hot is the opposite of what? Cold, right? So magnets have this thing called magnetic poles, where one side clearly has to be north and one side clearly has to be south. Now, you may have heard that a magnet has these invisible fields around it. It's these magnetic fields that your eyes cannot see. But scientists have done experiments over the centuries, and they were able, even though you can't see these magnetic fields, these magnetic fields, which, how you say, carry the magnetic force, right? They have found through experiments, we won't go into the experiments right now, that magnetic fields flow from north to south. Now, if you look at my first diagram, right, you will see a magnet. One side, like I said, is north, N for north, and one side is south. You notice the magnetic field lines, they flow from north to south. You'll see that they have the arrows going from north to south. And the truth is that there are billions of magnetic field lines that go around the magnet, and all of them flow from north to south. But obviously, when you're drawing your diagrams today, I don't want you to draw a billion lines. We might not have enough time for that. All right. So, some of you are probably wondering what's going on with these broken lines. Like this line goes here, and it doesn't seem to connect to anything. This really means that it's flowing from north to the south. But it's so large that the loop is so large, it can't actually fit on the paper now, right? But just keep in mind, and just for introductory purposes, that magnetic field lines flow from north to south, all right? So I want everyone to draw this diagram only. Do not draw the other diagram. The other diagram has a mistake in it, right? Anyway, everyone draw this diagram for me. You don't have to draw 1, 2, 3, 4. You can just draw a couple, like, I'm gonna tell you which ones you can draw, right? To make the diagram simpler. You could probably draw this one, this one, this one, this one, this one, and this one. The ones I put a dot by, right? That should be enough. You don't need to draw all, I guess I'd have about 12 lines there. You could just draw about 6 of them. The general idea is this, and I don't want you to think the topic is complex, is that magnetic field lines flow from north to south. And magnetic field lines, like whenever you hold a magnet in your hand, the magnetic field lines are obviously invisible. But if you do your experiments properly, you will realize these invisible lines flow from north to south. Simple concept, right? When you're finished drawing the first diagram only, raise your hands, all right? So I'll know how to gauge the pace of the class. All right, so let's go at the second diagram now. Like I said, there's a mistake in it. Now, for the second diagram, we have two magnets next to each other. Now, two magnets, two things can actually happen. If you put two magnets next to each other, they either attract each other or they repel each other. Repel means to push away each other. Now, I just go in with common knowledge, right? Magnets, opposite sides attract. And I have a little slide with that on the next page. But opposites attract, meaning that a north is attracted to a south pole. Like if you take two magnets and the north pole, like this one here, is facing the south pole, the two of them will attract, the two magnets will pull each other together and they will collide with each other like an accident. Now, it doesn't matter if I have one magnet, two magnets, or 10 magnets. Magnetic field lines always flow on the outside of a magnet from north to south. Remember the first diagram? Magnetic field lines flow from north to south. So it doesn't matter if I have two magnets. Look at this. For the first magnet, I have a few lines going from north to south, right? Notice this here. You will see north to south. But there's a mistake in this diagram. Look at this here. I have a north. Here has a north, and here has what? A south, right? You notice this magnetic field line on top is correct. His arrow is in the correct direction. All north, there must be a magnetic field connecting all north to south combinations. I have the correct thing here, north to south. But you notice I have a little mistake here. Look at this line here. Is the arrow in the correct direction? No. This magnetic field line is going from south to north by mistake. I made a mistake in this diagram, right? It wasn't intentional. It was a genuine mistake, right? Do you all see any other mistakes there? Look at down here. I have it in the wrong direction. This one here going from south to north by mistake. The arrow's supposed to be this way. Magnetic field lines are always, and only flow from north to south. In the exam, right? When it's time for your term test exam or your CXC exam, the examiner will ask you to draw these field lines. Like he might put one magnet, he might put two magnets, okay? Now, there are plenty different combinations. I'm not going to do all today to bore you. We could do that when we almost finish the topic. For the time being, I just have two combinations, a single magnet and two magnets where the opposite poles face each other, right? Right? So do me a favor, draw the second diagram. And yes, obviously you have to memorize it, right? You have to memorize the patterns for the examiner, right? If you all see any other mistakes, I don't think there are any other mistakes on the diagrams, but you feel free to let me know. Oh, by the way, we use the chat. Microphones and videos are disabled, obviously, for security reasons, right? So you will see somewhere on your screen where you can send messages to me, the host. Only I can see your messages. Public chat is disabled, obviously, for security purposes. You know how people are, right? So whenever you send a message to me directly, only I could see it, right? If your chat is disabled, there's nothing I could really do about it, unfortunately. That is an issue on your end you need to see about, right? Meaning that you might have to download the Zoom app itself and try to log in using the Zoom app rather than logging in through a browser, right? But you can always research that for after class on how I say set up your computer and Zoom on your particular device to make sure the chat is enabled, right? All right, somebody spotted the mistake. You all see something here? The magnetic field lines are leaving the north here, right? This is correct, not a problem. Remember, they're going all the way around and it's supposed to come on this side. These field lines are supposed to be flowing towards the south. All of these in the wrong direction. Very good spot, guys. Very good spot. Because these field lines are really big and coming around. They are flowing from north into the south. The same thing here. This one leaving the north and going to the south. So whoever spotted that, well done. Right? I was using AI to make the images now, but the AI makes little mistakes now. Right? Somebody spotted our next mistake. Thank you. And it's good, huh? Look at this one on top. How come only one person told me about this? This one going from south to north. Isn't it supposed to be the opposite direction? Very good spot. Very good spot. Right? Actually, I'm kind of glad now the AI made some mistakes. It really shows me Who's paying attention, right? And who is really investing themselves into the diagrams, right? When you finish, raise your hands, right? We have much more interesting things to do today. Magnetic fields around magnets is the most boring part of this topic, right? So let's get this out of the way before I fall asleep. All right, so I'm getting ready to move on in 10 seconds, right? Right. If you need me to go back to this diagram at the end of class, no problem, right? But like I said, you have much more interesting things to do. All right, so let's move on to the next slide, okay? And this is, well, some basics here. Well, what you need to remember is opposite poles attract and like poles repel. So we have three quick situations here, even though I know a lot of people know this, right? If you face a north and south pole together, like if you have two magnets and you organize it such that the north pole is facing each other, look at the arrows. The two of them will what? Attract. Simple. If you put a south pole and the south pole is facing the other south poles, right? Those are like poles. Like poles mean the same now. So two south poles will what? Repel. And similarly, if you put a north pole that is facing another north pole, like poles repel. I know this seems like a very simple concept, right? And you might say, but I know that long time, right? Still take down the diagram. Because I guarantee you, when we reach the harder sections, even a simple stuff like this, you will start to forget it. You will start to falter on it, right? Believe me, I know I've done this many years. You will start to falter on it. So even if you think you know it, draw the diagrams, take down the note. Opposite poles attract, like poles repel, right? When you finish, raise your hands so I'll know how to move. All right, take about 20 seconds again, and we will move on, right? Right, so keep telling yourself this over and over, right? Especially if you're new to the topic, right? Opposite poles attract, once the two poles are different, north south or south north, they're going to attract. If they're the same, they push each other away, right? All right, let's get to the next slide, right? Always go back to this at the end of class, right? Right, so this is where the fun starts. Everybody knows what a compass is. You know, like when you go camping or you're going exploring in the woods, even if you never went exploring in the woods, I'm sure you saw many TV shows where people use something called a compass. This guy here is holding a compass. And a compass, right, tells you if you get lost, which direction is north and which direction is south. Now, you ever wondered, you probably had more important things to do in life than sit down and ask yourself, hey, I wonder how a compass is worked, right? How does a compass know which direction is north? All right. Well, I'm going to explain the concept. And you're going to realize by understanding this simple concept, you're going to realize that something that you taught about your whole life was probably wrong. So you're going to learn something amazing here today. All right. A compass has a needle. In case you can't see the needle properly, I'm just going to highlight the needle here. That needle will spin and tell you which direction is north. What a lot of people don't know is that the needle is actually a magnet, right? That little, that little needle thing here, the silver thing, is actually a magnet. And what do we know about magnets? From the previous slide, we just learned that opposite poles attract and like poles repel. Okay? So let's go to the Earth, right? Here's a little diagram of the Earth. We all know Santa Claus lives in the North Pole. So that's Santa Claus there on the North Pole. I don't know why he looks like that, right? And Antarctica, with all the penguins, they live in the South Pole. All right? So basic information. When you use a compass, I'm going to draw back this needle. I'm just going to draw an arrow. In magnets, right? Anytime you draw an arrow to represent a magnet, like anytime, the arrowhead is always north and the tail is always south. Like that's if you're too lazy to draw a full rectangle for a magnet now, and you just want to draw an arrow to represent the magnet, the arrowhead, once again, represents the north, and the tail, the end of the tail, represents the south. So here's what happens. When you take this magnet, it's supposed to point in this direction, and everyone agrees with that. The arrow will point this way. But something doesn't make sense here. The top of the arrowhead is north, and the tail is south. If here is the North Pole, that means the top of my compass, my north, is attracted to north. That's why it faces north. And the tail of my compass faces south. Remember, this is the South Pole where the penguins live. But anybody realize that something is wrong with this diagram? How come north is attracted to north? And how come south faces the south? Because this suggests that south is attracted to south. But didn't we just say opposite poles attract, but like poles supposed to repel? So how come my North Pole is attracted to the North Pole of the Earth? Why is it attracted to where Santa Claus lives? It seems like that is the opposite. Here's where the confusion lies. The first thing you have to know, and a lot of people don't know this, especially if you're new to science, did you know the Earth is a huge magnet? How much people did not know that? Raise your hands. The Earth that we live on is actually a huge magnet. That's right. In fact, most planets in the solar system are magnets, right? I know it's made up of rocks and lava and whatnot, but when you put all of those things together, it just happens. We create a magnet. So that means Jupiter is a magnet, Pluto is a magnet, Mars is a magnet. Now, all magnets must have what? A North Pole and a South Pole, right? But it's our language that causes the problem. There are two types of north: geographic north, that means directional north, or magnetic north. The Earth, like I just said, is a huge magnet. Where Santa Claus lives, it's a huge South Pole, a magnetic South Pole. And where the penguins live, it's a huge magnetic North Pole. So a lot of people think where Santa Claus, even though, let me just say you always knew that the Earth was a magnet, right? Let's just say you always knew that. Where Santa Claus lives, even though he lives in geographic north, that's directional north, the top of the Earth is actually a magnetic South Pole. And where the penguins live, even though that's a geographic south, that's geographic south, it's actually a North Pole. So that is why your compass north is attracted to the top of the Earth, because the top of the Earth is a south magnetic field. And the underneath of your compass, which is a south, is attracted to the base of the Earth, because the base of the Earth is a magnetic North Pole. Now, every 100, roughly 100,000 years, the magnetic fields switch. So we living in a time, we just happen to be living in an era where the top of the Earth is a magnetic south and the underneath of the Earth is a magnetic north. But your great, 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 great grandchildren, 100,000 years from now, their compass will behave opposite, because when your super great grandchildren are alive, the magnetic south pole will move back down to the penguins and the magnetic north will move back up, right? So every 100,000 years, it switches, right? So do me a favor, guys. I hope that was mind-blowing, right? So I want you to take down everything on the screen. Yeah, I want you to draw Santa Claus. I want you to draw the penguin. I want you to take down the note at the top, the note at the underneath. I want you to take down the heading, and I want you to make a note that the Earth is a huge magnet. So anytime somebody tells you, could you please move north? Please ask them to specify. Are you talking about directional north or are you talking about magnetic north? Because if they are asking you to walk north and it's magnetic north they're talking about, they really want you to walk to Antarctica. I know you're not going to do that, right? But just say it, right? Anytime somebody asks you, hey, could you walk north? From now on, I am going to ask them to specify. Good sir, could you please specify if you mean magnetic north or geographic north? Because that would greatly decide where I am to walk. Let me know when you're finished with everything on the screen, guys. Right, so while you guys take that down, I just want to talk to the people on YouTube. On YouTube, right, I'm trying my best to monitor the chat, right? But you're always going to meet some fool, a troll now, who's begging for attention on the chat, right? And every year you just get a clown like that, right? Here's what you need to do. Don't reply to them. The minute you reply to them, that's exactly what they want. They're seeking attention, right? I would eventually remove them, right? It takes me like a minute or two to check. But the minute you respond to them, you're going to start distracting yourself. You're going to start distracting the class. Do not respond to anything absurd on the chat. You just need to answer the questions. And eventually, the troll, even if I don't catch them, when they realize, wait, no, they're not getting any attention here, they will move on. They will log off. Okay? Right? And of course, any trolls, I do report them directly to YouTube and make an official report to try to get them banned permanently, right? So after class, so I will deal with them, right? So don't worry about trolls on the chat. Right? Raise your hands when you're finishing, guys. Raise your hand. So someone asks if the sun, just like all the planets, if the sun itself is a magnet. Yes, the sun is a magnet, right? The sun is actually the large one of the largest magnets it has, right? Mm. I know some of you are asking the question, what makes all the planets a magnet? Like what it have inside the planet that makes it a magnet? It's kind of complicated, but it has to do with the molten lava and the molten stuff, the hot liquid as you go towards the center of the earth, right? It's a little bit complex to explain for this class, right? But that should give you a little jump start. Let's go, guys. Let's go. Let's go. Right. So let's see the next slide here. Right. What? Right. So you ever wondered why a magnet is a magnet? But think about this, right? Why are certain things a magnet and why are certain things not a magnet? First of all, let's just clarify something, right? Um, there are only certain materials which are attracted to a magnet. A lot of people think magnets attract any metal. For those who like to play around with science stuff and whatnot at home, like you like to break apart speakers and break apart TVs and go through the electronics and thing inside a TV or a radio, like you like to do those kinds of things. You would have realized by now, not all metals are attracted to magnets. Like this thing, aluminum. You know, aluminum foil? You know, well, aluminum foil is aluminum. Aluminum is a metal. Magnets are not attracted to aluminum. Gold is a metal. A magnet doesn't attract gold. Silver is a metal. Magnets could care less about silver. On the syllabus, right, there are only 4 types of metals that are attracted to magnets. And these are the 4 metals: iron, steel, nickel, and cobalt. Most people might not know about the last guy, cobalt, but cobalt is a type of metal. Well, when we're doing chemistry, you're going to hear him being mentioned, right? So, but the next question is, why are certain materials magnets and why are certain materials not magnets? Like if you hold a straw or a pencil in your hand or a piece of plastic in your hand, that's not a magnet. Why? And that's going to boil down to something on the atomic scale. But before we do that, let me explain something with forces. You all know a force is a push or a pull. Some people are stronger. They can push people stronger or they can pull someone. Let's say we have a basket of fruits here, right? But by the way, in case you didn't know, forces are measured in something called NEW, called newtons. The symbol for newtons is the letter N. In case you didn't know, you can measure almost anything in science. You can measure almost anything. And you can measure length in centimeters or time in seconds or temperature in degrees Celsius. Well, you can measure forces or how strong someone is in newtons. So let's say we have a basket of fruits here. And let's say you have someone who decides to push it. Yeah, they have extremely long hands there, right? So this person is trying to push this basket. Now I'm going to use an arrow to represent this. Let's say one person is pushing this basket at 10 newtons. So that's his strength. And then another person decides to help him. And he decides to push at 7 newtons in the same direction. Tell me something. Will the total force be 17? What does common sense say? That if 2 people are pushing in the same direction, is it okay to add their forces? I'll repeat that. Is it okay to add their forces to get a larger force of 17? What do you guys think? Does 2 people, sorry, not does, do 2 people pushing in the same direction make it easier or harder? What does common sense say? Let's use common sense. This is not actually a science question. That's common sense. Right. And the answer is yes. Whenever 2 forces are in the same direction, let's just say the other person is just as strong. Let's say his force was also 10 newtons. And you could add these 2 forces to get one force of 20 newtons, because 10 plus 10 is 20. The point is, whenever forces are in the same direction, they add up to give you a larger force. But what would happen now if the second guy came and said, hey, I'm going to push in the opposite direction? Will that crate of apples move? If one person is pushing to the right at 10 newtons and some other person says, let me help you, and he goes on the other side and he pushes in the other direction at exactly 10, will that crate of apples move? No. Won't the 2 forces cancel out to give you 0 newtons? In real life, the apple crate will not move. So the moral of the story is this. When forces are in the same direction, they add up to give you something stronger. When forces are not in the same direction, in other words, one example of not in the same direction is opposite directions, they usually cancel out to give you nothing, right? Let's use that concept to understand why certain materials are magnets and why certain materials are not magnets. Right? I'll leave that diagram there just in case you want to view it. Let's take a normal piece of iron, right? A piece of iron, a normal piece of iron is not a magnet. Don't get me wrong, iron is attracted to magnets, but a piece of iron itself, like if you go on the ground now and you find a piece of iron, or you go in the garage and you find a piece of iron, that piece of iron is not a magnet. But why? Here's the thing, right? All things are made up of smaller things called atoms, right? Everything is made up of smaller pieces called atoms. Quick question. If I take a magnet, let me say I have a magnet here. One side is north, one side is south. If I break this magnet, let's say I get angry and I break that magnet into two pieces, will it spoil the magnet? Answer that question for me first. If I take a big magnet and I get angry and I break it into two pieces, will that spoil the magnet? Yes or no? Will it spoil? Right? That's a reading truth, right? The answer is no. Breaking a magnet doesn't spoil a magnet, right? Let me get that on the recording. Breaking a magnet doesn't spoil a magnet. In fact, if you take a big magnet and break it into two pieces, you just get two magnets. And if I take this broken piece here and I break that into two pieces, I will get two smaller magnets. So every time you break a magnet, you just get a smaller magnet. So let's say we do that a billion times. We break the magnet and we take the broken piece and break it again. And we keep doing it over and over and over. Eventually, you will reach the atomic scale where you will get a magnet so small that you can't break it again. The smallest possible magnet is called a magnetic dipole. Okay? That's the smallest possible magnet. Let's, just for simplicity's sake, I know somebody's going to ask, well, what would happen if you break the smallest magnet? Like if you take a magnetic dipole and you break it in two, what will happen? The short answer is it will explode. That's how they create atomic bombs, right? But we're not going to get into that right now. Now, the general symbol for a magnetic dipole is an arrow. Well, whenever you see like a diagram of a magnet and you see arrows inside of a magnet, they represent this thing called magnetic dipoles. The arrowhead represents the north as usual, and the end of the tail is the south. Now, here's the amazing thing, right? If you were to take a piece of iron and put it underneath a very, very, very powerful microscope, let's say we had the most powerful microscope in the world, you would see technically that the iron is made up of a whole set of magnetic dipoles. So look at this diagram here, guys. You notice that I have a whole set of arrows inside of it. All these arrows are what? Magnetic dipoles. And you notice that something else. These dash lines are invisible lines, by the way. You don't see these dash lines. This is like an area. Just like how Trinidad is divided up into different areas. What are the different counties again? It have St. David, it have Caroni, it have St. Patrick's. I forget where I think you call it counties or districts or whatnot, right? In a piece of iron or inside something that is not a magnet, you realize that inside non-magnetic materials, certain regions, like in this region here, all the dipoles face the same direction. And everybody in this area face the same direction. The general areas, right, are called domains. Look at here. So how much domains does it have in this material? It has 1, 2, 3, 4, 5, 6. There are 6 domains, and everybody who lives in a certain domain, the dipoles that live in a certain domain, they always face the same direction. Which brings up a real important mind-boggling question. If a piece of iron is made up of smaller magnets, remember, the small arrows are magnetic dipoles. If a piece of iron is made up of magnets or magnetic dipoles, how come a piece of iron is not a magnet? That doesn't make sense, right? Because if I tell you your entire body is made up of magnets, and then I say, even though your body is made up of billions of magnets, you are not a magnet. Any of you that's watching me like I crazy? How could somebody be made up of, it's like telling somebody, hey, you are made up of water, like you have a bucket of water, but your bucket of water is not water. That's craziness, right? Let me explain why, right? It's not actually that crazy once you understand. You notice that the dipoles are facing in different directions. So this dipole will have a magnetic force. This set of dipoles will also have a magnetic force. But because the dipoles are all facing different directions in different domains, all the magnetic forces cancel out. Remember the situation with the situation here with the apples? If people were pushing in different directions, the forces do what? Cancel out. It's the same concept here. You have plenty magnets, each have a magnetic force, right? Magnets provide a magnetic force. But because they are all facing different directions, when you add up their forces, they cancel out and it come like you do have a magnet, right? So that's the reason why. In a magnet, in a true magnet, look at the diagram here. You notice all the dipoles. If you visit each domain or each area, you notice it have unity. All the dipoles are facing the same direction. So that come like everybody is what? Pushing the same direction. And when everybody is pushing the same direction, all the forces add up and you get something strong. So the only difference between a piece of iron and a magnet is that the dipoles are facing in the same direction, which is amazing, which means if we were to find a way, like if we were to go and have a word with Mr. Iron, we say, hey, Mr. Iron, what's going on here? All your dipoles face in this different direction. What kind of madness is this? You have no control over your dipoles. Do something here. If the iron were to say, all right, fellas, everybody, face the same direction. If the dipoles listen and all of them face the same direction, the piece of iron will change into a magnet. That goes for any material in the world. Eh? If you have any material in the world, right, and the dipoles are not facing the same direction, it's not a magnet. But if you found a way to get all the dipoles to face the same direction, that piece of material will magically change into a magnet. And one side will become north and one side will become south. The side the arrowheads are pointing to will be the North Pole. And the sides the tails are facing will become the south. Take down everything on the screen. Draw neat diagrams. You don't need to take down the apple part, the diagram with the apple case, right? Let me know when you're finished. I hope that was a good enough explanation. Right? When you guys are finished, raise your hands and draw nice diagrams. And guys, don't draw all how diagrams, right? So you all know the difference now between, right, a regular piece of material and a magnet, which means the earth is a magnet, right? So that means when you go down into the center, as you approach the center of the earth, remember there's a lot of molten liquid, a lot of hot things, right? Um, there are dipoles floating around the center of the earth. And it just so happens the dipoles, most of them face the same direction, which is why the earth is a huge magnet, right? It's one of the reasons, right? Like, that's a simple explanation. I know somebody's going to AI it or Google it and say it have a little bit of flaws in my answer. I remember it's a beginner's class. I can't go into the real specifics. I will just end up confusing you all too much, right? So, bear with my simple layman's explanations for the time being. Right? So I just want to let you know that even though it may be obvious, when you put iron, steel, nickel, and cobalt underneath a very powerful microscope, the dipoles, you will see dipoles, but the dipoles will be what? Facing in different directions, right? All of them. I know I use the explanation for iron only, but it's the same explanation that applies for steel, nickel, and cobalt. Right? Raise your hands when you finish. So far, 64 people are finished. All right. Don't worry. After this, we'll take a little small, I say, we'll play the little game now where we're gonna vote on your superhero characters or whatnot, and we're gonna try to earn points for the teams. I'm gonna get my pen and pencil here to take notes of the point. Remember, the blue team is in the lead as usual. Right. My mission in life is to bring down the blue team. That's my mission. Right. I'm giving you guys 1 more minute. I know some of you, you're taking your time with that diagram. So you have 1 minute. Gonna move on. Right. So that's one that addressed something. And somebody, it's a good point. It's a real nice point. You all notice that in this diagram, look at the diagram underneath. I said that magnets flow from what? Magnetic field lines, or the arrows supposed to go from what? North to south. If you look at this diagram here, let me draw it back neater for you guys. Remember, I'm saying this side is south, right? Let me get this on the recording. It's a real good question. I said from the earlier diagrams that magnetic field lines flow from how? North to south. So if I had a magnet like this, would this be in the north and this is the south? The magnetic field lines, or the arrows that represent the magnetic field lines, flow from what? North to south. But in this diagram, you notice if here is south, because the tails represent the south and the arrowheads represent the north, it looks like the magnetic field or the arrows are flowing from where? South to north. That seems to be the opposite of what I have been saying. But I'm not wrong. All the magnetic field lines you drew so far, think about it. Did you draw it on the outside of the magnet or the inside of the magnet? Magnetic field lines, and I was going to explain this a few slides down, right? I didn't forget it. It's just I was leaving it. I didn't think somebody would have picked up on it. On the outside of a magnet, magnetic field lines flow from north to south. But on the inside of a magnet, it's the opposite. It flows from south to north. So that's a good pickup for the person who saw that, right? On the outside of a magnet, magnetic field lines, or the arrows, go from north to south. But on the inside, if you were to go inside the magnet, it goes from south to north. All right, but you're going to have a whole note on that a few slides down from now. All right. So anyway, good question. All right, so let's take a little break here, right? Let's launch. You all know how to play this. So what we're gonna do, two superheroes are going to appear in either A or B. Just 1 second, guys. All right, get us to the top here, right? And you all are going to vote whichever one wins. Well, you're gonna get points for either for two of the team. Let's go. I hope we get two cool ones. Let's do our next one. You all don't know who this is. That's the Beast from Beauty and the Beast, and that was Nightcrawler. I like this one. All right. So it have Mr. Bean, right? You all know Mr. Bean, the comedian, Johnny English, one of the coolest characters of all time, in my opinion, or Iron Man. Believe it or not, I'm not an Iron Man fan, right? So think about it, guys, and I know a lot of people out there are not Iron Man fan, right? So we're gonna launch the polls in a little while, right? And we're gonna vote. Are you gonna vote for A, Mr. Bean, or Iron Man? Right? Think about it, and I'll launch the polls in a little while. You know who I voted for. I voted for Mr. Bean. He's the coolest. All right. Vote, guys. Let's see what you come up with. Right? Those on YouTube, let me know. A or B, Mr. Bean or Iron Man. You can't go wrong with Mr. Bean with his little baseball back there. That's a true superhero. But you all decide. Guys, it's super close. Like it almost even here. Everyone put in a vote so we could sway it. We could swing this. Mr. Bean could win at this point or Iron Man. Come on, guys. There are 40 more people to vote, and it will make a difference. It will make a difference. All right, let's end the polls here. Well, it actually went the way I wanted it to. And I really didn't think Mr. Bean would have won. But Mr. Bean got 57%, so that's option A. And Iron Man wasn't far behind with 43%. So let's see what points are associated with Mr. Bean. So let's click on A. Keep your eyes to the top of Mr. Bean. The yellow team got 2 points and the red team got 14 points today. Not bad, green team. We're real suffering. When I say we, because I'm part of the green team. So the red team, they have 14 points, and the yellow team, you have 2 points so far. Sorry, green team. We'll get some points hopefully later on. So congrats to the yellow team and the red team, right? 2 and 14 in that order. All right, let's move on. All right. So we're going to talk about something called magnetic induction. All right? Remember we said something that there are 4 materials that are attracted to magnets. Remember, it have 4. What's it for? Iron, steel, nickel, and cobalt. It have 4 materials. Now, usually we say it's slightly wrong. And I know even when I tell you the correct thing now, you're still going to say the wrong thing when you go out in public. It's actually not correct to say iron is attracted to a magnet. It's actually not correct to also say steel is attracted to a magnet. Let me explain why. The only thing that's attracted to a magnet is actually another magnet. Let me say that back because it probably went over your head there. The only thing attracted to a magnet is another magnet. So let's do a little experiment here. Here we have a magnet. How do we know this is a magnet? Look at all the dipoles, and all the dipoles are facing the same direction. It have unity here, right? It have unity. Everyone facing the same direction. And by looking at this here, let me just say the examiner were to draw this in the exam. And he were to ask you, which side of this magnet is the North Pole and which side is the South? That's easy. The arrowheads point to the north side and the tails point to the south side. Okay? Magnetic field lines around the magnet flow from how? North to south. Now remember, I have billions of these lines here. What's going to happen is that when you bring a magnet close to a piece of iron, initially the iron is actually not attracted to the magnet. I know you're probably saying, but sir, I know iron is attracted to magnet. But hear the story. When the magnet goes close to the iron, initially the iron is not interested. The iron will say, oh, you're just a magnet. I am not attracted to you. I am not going to be pulled towards you. But here's what the magnet does. Remember, the magnet has magnetic field lines, these field lines flowing around it. Now remember, it has billions of them, right? So eventually some of these field lines are going to cross, or how you say, interact with the iron. Remember, these are magnetic field lines. They have a certain force, or they have a certain influence. It comes like peer pressure, right? So what's going to happen in the iron, the dipoles are not facing the same direction. So the iron is not a magnet as yet. Remember, the only thing attracted to a magnet is another magnet. That piece of iron is not a proper magnet because the dipoles are all in different directions. The forces cancel out. But when these magnetic field lines begin to interact with the iron, remember, it's like peer pressure. Look at what's going to happen. The piece of iron, the dipoles are going to fall in line. So the dipoles, which were initially, the dipoles, which were initially in different directions, they fall under the spell of the magnet or the peer pressure of the magnetic field lines. And all the dipoles begin to line up and face the same direction like zombies, right? Which means now the iron is officially a what? Magnet. And it will line up in such a way. Here will be north and here will be south. Look at it. The tails are here, the heads are here. And because you have a south pole here and a north pole here, the two magnets now will attract. So you all see what happened there? The magnet peer pressured the iron into becoming a magnet. The magnet says, hey, get your dipoles in line and become a magnet, so we are attracted. That peer pressure or influencing another material to become a magnet, so attraction happens, you call that concept magnetic induction, or I like to call it magnetic peer pressure, right? But that's just my word for it. So that is what actually happens when you bring a magnetic material next to a magnet. The magnet changes that material into a magnet first by forcing it to rearrange its dipoles. So it changes into a magnet. And once both of them are become a magnet, attraction happens. Okay? Now, you don't need to draw the diagrams, right? You just need to take down the definition of it, right? So take down the note on top. Magnetic induction is when a magnet influences another material to become a magnet. And it does so by using its magnetic fields, right? Its peer pressure fields. Okay? Let me know when you finish taking down that note. It shouldn't take you too long. There's no need to draw the diagram. Okay? So once again, for those who didn't, well, while I take down that, magnetic induction is when one magnet influences another one to become a magnet. Right? Guys, if you're getting problems with audio and visuals and whatnot, right? Remember, the problem is going to be most likely on your end, right? So messaging me about it is not going to help, right? Whenever my audio or something is giving problems or my internet is unstable, I will get a warning on my end, right? So if you are getting issues on your end, the quickest, most efficient way is to check your end for any problems or log back out and log back in, because I guarantee you the issue won't There's 99% sure the issue is not on my end. I will get a warning on my side. Zoom is pretty good at warning me when something is wrong on my end. Right? All right, let's go. That wasn't a long note or anything like that. All right, let's go. Right. So how do you make a magnet? Right? Remember, what makes a magnet a magnet? Once you get the dipoles to face the same direction, it becomes a magnet, right? And isn't that the key to being a magnet? To make sure your dipoles are facing the same direction. Now, there are three ways. So when I was small, I used to do all of this as experiments at home for fun. Because back then, it didn't have a PS2, it didn't have PlayStation, it didn't have no Xbox. And my father wasn't going to buy any of that for me. So I had to find other ways to entertain myself. So one of the favorite things me and my brothers used to like to do, we used to like to create magnets or make magnets. So how to make a magnet? Well, all you have to do, one of the easiest ways is this. If you take a piece of iron and you have a real magnet, all you have to do is rub the magnet, the real magnet, on a piece of iron, but you have to rub it in one direction. You can't rub it this way and then this way and then up and down or all how. What happens when you take a real magnet and you rub it on a piece of metal in one direction? The dipoles, which are initially mixed up, the magnetic fields from this magnet will eventually bring order to the chaos. It will, if you rub it enough times, that's probably about 20 times, the dipoles do what? They begin to line up. And what it doesn't take long, it might take about less than a minute to do that. And that piece of metal, for a little while, if it's a piece of iron, it will become a magnet for about 5 minutes. And then, well, iron has a way that after about 5 minutes, the dipoles, like if you move away the magnet, the piece of iron will go back to being disordered. The dipoles will, you know, it's like a teacher. When a teacher is in class, right? The students pay attention, everybody faces forward, right? Because you have the influence of the teacher. But when the teacher leaves class, after about 5 minutes, everybody say, well, teacher not here, no. We can do what we want. And then you get chaos, okay? So that's one easy way of creating a magnet. But to create a magnet in this case, you need a real magnet to start off the process with. But let's say you don't have a real magnet. Here's an easier way to do it. You could take a piece of metal and you just hammer it or hit it, but you have to hit it in one direction. Why does that work? Initially, the dipoles are mixed up, but if you hit it, you physically, like if you hit it in one direction, eventually you'll hit all the dipoles to face one direction. It's literally that simple. After class, you all could try that. Go and find a piece of iron and just get a hammer, and gently hammer it in one direction. One direction. You can't mix it up. Do it for about 5 minutes. And then you will see it will change into a magnet. You can bring some paper clips next to it and it will attract the paper clips. But once again, if you use an iron to do this, after 5 minutes, the dipoles, even though initially they will face in one direction, after 5 minutes, the dipoles will be like, let me go back to being disorderly. And it will change back into a regular boring piece of what? Iron. Another way to create a magnet is to use electricity. You just get a battery and you take the piece of iron and you wrap wire around it, right? Real simple. So one side goes to the North Pole, not the positive side of the battery. One side goes to the negative side. When you run a current around a piece of metal, you just also get a magnet. The dipoles just begin to straighten out. Don't worry about why too much as yet. All right, don't worry about it too much. It have plenty explanation later on to explain why. But you call this an electromagnet because you're using electricity from the battery to create the magnet. But you have to use something called a DC current, which comes from a regular boring battery. There are two types of current, one called AC and one called DC. Don't worry about the difference between AC and DC right now. On the next slide, I will explain the difference between AC and DC. Just know that regular boring batteries that you find in your house, like your Duracell battery, your Ever-Ready batteries, they produce DC current. Okay? So you don't need to draw the diagrams. The diagrams are too complex to draw. I just needed to take down the heading and the three ways to create a magnet. All right? When you finish with that, just raise your hands. Those are the three ways to create a magnet if you are bored at home. Right, 1 more minute and we're moving on. All right, let's get ready to move on. I think there's enough time to take down that small note. Remember, you were not supposed to draw the diagrams. All right, so we just spoke about how to create a magnet. Suppose you want to destroy a magnet, right? Let's say Magneto comes to attack you. Well, he's basically, let's just assume, I know he's not a magnet. I know he could just control magnets, like, but let's just assume Magneto is a magnet. How would you destroy him, right? This would be very, very useful information for the, I guess it's the Avengers. I don't even know. I don't follow superhero stuff, right? So here's the three ways to destroy a magnet. The first way, if somebody gives you a magnet and you don't want it to be a magnet, all you have to do is hammer it, but in different directions. Just start to hammer it in all directions, forward, backward. you see, remember, what creates a magnet? And hammering it in one direction. But the minute you start to hammer that or hit it all how, the dipoles will become disarranged, you'll become confused and start to face different directions. And it will cease to be a magnet. Another way to destroy a magnet is to use the opposite of DC current. Remember I tell you there was two types of current, AC and DC. I will explain the difference just now. But if you push a AC current around a magnet, it stops being a magnet. So if DC creates a magnet, the opposite of DC is AC, will destroy the magnet. And another way is to heat it. If you take a magnet and heat it and let it cool down, it won't be a magnet again. All right? So that's one way of destroying a magnet. I'm not saying burn it up. All you have to do is heat the magnet, make it hot, and let it cool back down. And when it cool back down, it won't be a magnet again. So no need to draw the diagrams. Take down this and the heading. How to demagnetize how to demagnetize a magnet. I made a small mistake on the heading there. How to demagnetize a magnet. In other words, how to destroy a magnet. All right, so if Magneto comes to attack you, you have three options. Take some hammers and then start to hit him. Or get Flash to run around him and wrap some wire around him. Quick. And then connect those wires to an AC supply. Or you throw him in a fire, right? And you heat up, and when he cool back down, he won't be Magneto anymore. He will just be a regular, boring Iron Man. That's a cool joke. Anyway, take down everything and take down everything. Let me know when you finish. I promise no more jokes from me. All right? No more jokes. All right, so that's the longest note in the world. So 20 more seconds and we're moving on. All right. Right, so I know a lot of people are sending questions. You know, the class is kind of huge, right? When you combine YouTube and so to be honest, I won't be able to get to all the questions. I have like over 200 plus questions pending, but you know, so sorry about not being able to. The free classes, they're really large, right? So you have to excuse me on, you know, not being able to answer all the questions. Okay. All right, so I just want to explain quickly the difference between AC and DC current, right? I'll just clear a little space over here, right? Um, let's clear a little space. So like I mentioned, there are two types of current. Let's say you have two pieces of wire. Here we have one piece of wire, orange wire, and I'm going to have a red one. Well, the red doesn't show there. We have a blue piece of wire. Whenever you hear DC, right? Whenever you have a DC current, DC stands for direct, D-I-R-E-C, that's it, current. That's what the abbreviation stands for. And DC means one direction. I know I spelled it kind of wrong here, but DC means one direction. The opposite of DC is something called AC current, which stands for alternating current. And effectively, AC means not two directions, not one direction, sorry, but two directions. You see, in a direct current, the current that flows inside the wire only flows in one direction. So in this case here, it's flowing from this side all the way to the other side. Alternating current, the current flows in two directions. Sometimes the current flows this way, and then it would reverse and flow the other way. Now, it doesn't flow both ways at the same time. It will flow one direction, the current that's flowing through the wire, the current that will shock you, right? The current will flow one direction, and then afterwards it will reverse direction, and it will go forward and backwards, forwards and backwards. So that's the difference between direct current and an alternating current. Direct current, once again, means the current is flowing in one direction all the time. It never changes direction. An alternating current is two directions, right? I have a slide with all of this soon, right? You don't need to take down that. I just wanted to introduce you to it because real people asking the questions. I'll say, how can I get out of the way one time? All right. Right. My mouth could use a break, right? So we're coming close to the end of class, right? Don't leave yet, guys. When I say that, people just begin to disappear. Stay till the end of class. There's plenty important things we need to talk about still. All right, let's do our nenext vote now. I'm real sour that the green team has not been getting any point. It's burning me. Right? So let's do another shuffle. Let's do another shuffle here. Let's see if we get two cool characters. Hey, not too bad. We have who's these two guys again? Well, that's the Pirates of the Caribbean guy, Jack Sparrow. And it have Marge Simpson from The Simpsons. I'm a huge Simpsons fan, grew up with The Simpsons, but I also like Pirates of the Caribbean. Think about it, and we're gonna launch the polls in a little while. A is Jack Sparrow. B is Marge Simpson from The Simpsons. Think about it. Let's get the polls going. While you all vote, remember, I don't share my slides right? I don't share the slides. What I do is, if you all check the channel, I do send the recording of the videos. So if you check the WhatsApp channel, by now everyone should be familiar with the WhatsApp channel because I told everyone who signed up about the WhatsApp channel. Your parents will know about it. If you go on the WhatsApp channel, you will see a link to get all the class recordings. But I usually don't share my slides, obviously for copyright purposes. Usually when I share my slides, it goes all over the place, and then other teachers, unfortunately take my slides. It's my property. So you can understand why I'm kind of protective about it, right? So you will get the class recordings. Obviously, not a problem with me. All right, guys, let's end the poll. One character has won by a landslide, and oh God, I was really hoping Marge Simpson would have won, but it seems that Jack Sparrow is more popular. Let's see what points are associated with Jack Sparrow. Green team, cross your fingers, cross your fingers. Let's see if we get some points now. Look above. Jesus. I don't know what's going on. But yellow team on 17 points. And red team, oh my God. Oh my God. Zero still for the green team. Zero still for the green team. Oh my God. Well, sometimes that's how life is, guys. That's how life is sometimes. You all can't say I rigged it, because my team is losing. All right, so we will tally up the points just now and whatnot, right? Now, here's something I need for you guys to know. It's a little table, right? It's a comparison between something called soft magnetic materials and hard magnetic materials, right? The term soft material and hard material doesn't mean if it's actually soft or hard, like sponge and metal. It refers to something else. You see, some metals are easier to magnetize than other metals. Remember, there are four magnetic materials: iron, steel, nickel, and cobalt, right? The examiner is not going to be too, it's not going to ask you any questions really on nickel and cobalt. They're only going to concentrate on iron and steel. Now, soft iron and iron is the same thing, right? It's the same thing. Don't let the word soft iron. But iron is regarded as a soft magnetic material, but steel is considered to be a hard magnetic material. Generally, a soft magnetic material, it's easy to magnetize it. That means if you have a piece of iron and you want to change the iron into a metal, remember I gave you three ways to create magnets. Iron is easier to change into a magnet. Steel, he's a hard magnetic material. It's kind of hard to change him into a magnet. You might need to use a stronger DC current, or you'll have to hit it harder with a hammer, right? But here's the trade-off. Even though iron is easy to change into a magnet, he loses its magnetism very easy. Steel, even though he's real hard to change into a magnet, once you get heat to change into a magnet, he will retain its magnetism for years, not 5 minutes like iron. If you have a piece of steel and you go today after class and you hit it with a hammer or you run a DC current through it, right? If you come back in 100 years, it will still be a magnet. It is retain its magnetism for very, very long, right? Now, those are only two differences between soft iron, which is a soft magnetic material, and steel, which is considered a hard magnetic material. But here's a table that you need to memorize for the exam. It's pretty self-explanatory, right? Um, you need to learn it off for the exam, right? In case you don't know what this means, retentivity, that means how long it will keep its magnetism once you magnetize it. Like iron, like I said, is low. It doesn't retain its magnetism for long. Steel has a high retentivity, meaning that once you magnetize it, it retains it for a very long time. Do me a favor, guys. Take down this table. Do not screenshot it. Take it down now. I'm giving you 5 minutes. We have time. We have the time, right? When you finish, raise your hands, please. Don't leave us yet, guys. We have one more thing to do, right? One more thing to do, right? I just need 5 minutes, just 5 minutes more for class and we're done. Right. So while you all take down that, right, you all can see the class. Well, the Zoom could hold up to 1,000 people, right? So you can see we have close to 500 spaces still available. So if you all know anybody who want to join the program from today, right, please tell them, message me, WhatsApp me. You all probably know my number by heart by now. I just writing it back on the screen. Just tell them WhatsApp me and they will automatically get to join the program from today, right? And of course, they will get access to the recording so they can watch today's work and get back on track and whatnot, right? Right. And remember, guys, keep checking the WhatsApp channel once a day for any updates, right? You have to check it and encourage your parents to check it, right? A lot of people are not checking it and they're missing out on all the updates and things. It's just once a day. Put on your notifications or something for the WhatsApp channel, right? Don't forget to raise your hands when you finish, right? Right? Oh, for those who don't have the WhatsApp channel link, I'm sending it on the chatter in case. When you go to that channel, if you scroll up, you'll see the link to access the recordings and everything, right? But you have to do your part. You have to go to the channel, just read a little bit, scroll up a little bit, right? You will see everything. Everything important goes on that WhatsApp channel, right? Make sure check your chat. Sending back the link here again. WhatsApp channel link. Check your chats and save the link. All right. All right. So about 70 people have finished. I also sent it on YouTube. So make sure and save the link, right? All right. So yeah, but I'll go back to this table just now, right? I just want to tally up the points. And for those who didn't finish the table, I'll stay back a few minutes again. But let me just tally up the points now. So today, the red team got a total of 34 extra points. So that means the red team are the new champions for the day, and the yellow team got 19 extra points, which brings the yellow team into second place. So that's the standings. Only my classes does the teams thing, and the other teachers don't use it, right? So any class with me, you will know it. So red team is first place, yellow team is in second place, the Vikings, blue team third, and unfortunately my team, the green team. Don't worry, guys, have faith. Tomorrow in chemistry class, we will get some points. I can feel it. All right. All right, so that brings us to the end of class, right? For those who want to stay back and take down the table, not a problem. I'll stay back for a couple minutes. And guys, please don't forget to tell people to message me now to get a spot in the program. We have 500 spots. All right. Take care, guys. Hope you learned a lot. All right. Have a good one. People on YouTube, hope you had a good time. All right, going to log off there now, guys. All right. So if you missed anything, don't worry. By tomorrow, the recordings will be posted up, right? I wonder if I have the link for the, oh, if anybody needs the link for the direct link for the recordings, I'm putting it on the chat here. All right, this is on Zoom. I won't be able to send it on YouTube. I don't have it saved on YouTube, right? The recordings are uploaded about 24 hours after class, right? If you happen to miss the maths class yesterday or the English class yesterday, guys, make sure and review the recordings, because you don't want to come to class next week lost. We're we're continuing from where we left off, right? And we're far from finishing magnetism and electromagnetism. We're going to be spending the whole summer doing this topic. It's a real long topic, right? Have a lot of calculations and whatnot we need to get to do later on. Right?